Hi, it's Mrs. Cat here to do a little wrap up of our solubility and solutions lab and to do a 3 levels diagram for solvation. So this is solvation with an O, not salvation. And the definition for this concept is the process by which solvent molecules surround and interact with solute molecules and ions. On this 3 levels diagram, we are actually going to start in the symbolic space of our 3 levels diagram, but we are going to change this to terms. We're not going to look at solvation symbolically, but we do have 3 definitions that we need to make sure that we get down before we can really talk about solvation and solutions. So the first one is solution. And we're going to define this as a homogeneous mixture. Now, remember, that means that if this is homogeneous, we've got one phase that we can see from, top to bottom in our mixture. It's going to look the same all the way throughout. It's going to have constant composition. Okay, the 2 parts of this solution that we will focus on are the solute and the solvent, and those will be our other 2 terms that we'll define in this space. Okay, so looking at solute first, this is going to be the substance that is dissolved into our solution. Now, you're probably most familiar with a solid solute, but a solute can be any phase of matter, just as a solvent can be any phase of matter. Okay, our solvent then would be the substance that dissolves the solute. Okay. Most of our experience probably at this point as science students has been using water as a solvent, which is exactly what we saw in our solutions and solubility lab. So we saw water being used as our solvent in the lab, and our solute was obviously the salt. Okay, we're going to go up to our macroscopic space, and we're going to look at the rate of solvation. This is going to be our conclusions that we can draw from the lab itself. I'm going to go ahead and split this into 3 regions because we're going to look at 3 different things based on our parts of the lab. One is temperature. Okay. The second is agitation or stirring. And then the third is crystal size. Okay, and these all match up to our parts of the lab. Okay, so hopefully what you saw in the lab itself with the rate of solvation and the effect of temperature is that as we increased the temperature, we saw a faster rate of solvation. Okay, and what that means is a faster rate of that solid salt dissolving. Okay, so some reasons for this. We're going to kind of circle back to some things we've talked about previously in the year. When we have a higher temperature of our solvent, we have more kinetic energy. Okay, remember, when we have more kinetic energy, our particles have more motion. And when there's more motion of particles, we're going to see more collisions occur. Okay, when there's more collisions between our solute and our solvent, that's going to give us a faster rate of solvation. Okay, so keeping that in mind, let's think about agitation or stirring and as what we saw and the reason behind that. So we should see, as we have more agitation, you should have also seen a faster rate. Okay, here it's the agitation that causes more motion of our particles, And then the increase in the motion causes more collisions. And that's what leads to a faster rate. Okay, finally, crystal size. We saw the opposite trend this time when we decreased the crystal size. And in the case of this lab, we had large crystals, we had normal size crystals, and a really fine crystal or like a powdered salt. This is what gave us a faster rate. Okay, reasons for this. When we have smaller crystal size, we have more surface area for the solvent to react or interact with the solute. And that means that we're going to have more space for collisions. With our solvent. Okay, and again, that's going to be exactly what increases our rate of solvation. Okay, so those are our 3 factors that we observed in our lab. Okay, temperature, agitation, and crystal size that have an effect on the rate of solvation. So let's switch to looking at solvation at the particulate level. So here's something that's really important. In order for solvation to occur, a similar attractive force must be present between our solute and solvent. Whoops. For solvation to occur. Okay, and again, remember, solvation is just our more scientific term for the process of dissolving to occur. Okay, so here's something we need to keep in mind, and that is the fact that we have water typically being used as our solvent. Okay, at this point, we should know how to draw a Lewis structure for this. We should be able to say that this is a polar molecule, which is very important. Okay, we've got oxygen that's going to be slightly negative due to its higher electronegativity of 3.5. Hydrogen is going to be slightly positive in both ends. Okay. We can also look at our water molecule as a particulate, not just a Lewis structure. Okay, so there's my particulate picture. Okay, again, slightly negative oxygen, slightly positive hydrogens. Okay, so we're going to see a couple of things happen. Okay, one is going to be an ionic solute, which will dissolve in a polar solvent. Okay, so I'm going to split this. Give myself some space here. And what I'm going to have here is, I'm just going to draw my 1 particle of my solute. And we're going to make this ionic, so there's a plus and a minus charge. And then I'm going to draw in my water molecules. So I'm going to draw in these as Lewis structures this time. Okay, and whoops, don't forget my lone pairs. What we're going to see is these water molecules are going to be attracted to the positive and negative ions because, again, let's mark this on one of these, slightly positive and slightly negative ends of the water molecule are going to arrange themselves so that we have a separation that winds up occurring of our ions. Okay. Now I'm actually drawing this backwards, but what actually happens first is these water molecules are going to surround the ions, and that will then cause the attractive forces between the water molecules and the ions will be stronger than the attractive forces between the ions themselves, and it's going to cause it to break apart. Okay, these water molecules will arrange themselves so that the slightly negative end of the water molecule is going to be attracted to, not attached to, attracted to the positive cation in this case. Okay, it's the green particle. And then our negative ion is going to be attracting the positive end, slightly positive end of our water molecule at the hydrogens. Okay. And again, let me mark one of these. Let's go slightly positive, slightly negative, slightly positive. Okay. We're going to see a similar pattern occur when we have a polar covalent solute. Okay. Now remember, polar covalent will have a slight positive and a slight negative end of the molecule. Let's see here. This isn't really what they're going to look like, but I'm just going to oversimplify this here. Okay, so I'm going to show this as slightly positive, slightly negative, and this time I'm going to draw my water molecules as the particulate version. Notice how I'm representing the bent geometry of the water molecule. Okay, and then let's mark one of these slightly negative, slightly positive, slightly positive. Okay, the main difference here is that our particles in this case, in a polar solvent, don't actually separate, okay, and cause a separation of charge or ionization, but instead we're still going to have the dissolving occur. Okay, we're still going to have the arrangement of our water molecules so that we have an attraction between the slightly negative end of the oxygen part of the molecule and the slightly positive end of our polar molecule. Okay, so we'll see that arrangement here. And then our slightly positive end of the water molecule will be attracted to and arrange itself around the slight negative end of the polar molecule. Okay, and then for good measure, let's mark one of these. Slightly negative, slightly positive, slightly positive. Okay. So that is our particulate representation of solvation. And that's going to do it for solvation. Up next is a look at solubility, and a wrap up with that with another 3 levels diagram. So stay tuned.